All right, today we're going to be looking at some motion on a line and critical points multiple choice practice. And for these first ones, we're not going to use a calculator. And then for the second ones, we would have access to it. It doesn't necessarily mean that we would use it, but we would have access. So let's start with this first one. A particle moves along the x-axis so that its position at time t is given by this function. So this is the position function. We want to know for what value of t is the velocity of the particle 0. So we first have to find the velocity of the particle. So we're going to find v of t. And our velocity function is the derivative of our position function, so 2t minus 6. And then we set our velocity equal to 0 because we want to know when, for what value of t is the velocity equal to 0. And then we solve for t, which is 3. All right, let's talk about the next question. So we have a particle moving along a straight line. The graph of the particle's position is shown above from 0 to 6 seconds. The graph has horizontal tangents at 0 and at 5 and a point of inflection at 2. For what values of t is the velocity of the particle increasing? So we can kind of think of this as this is our original graph, right? Then our velocity would be our first derivative, and then our acceleration would be our second derivative, which means if we're looking for where our velocity is increasing, so if you're looking for where the first derivative is increasing, that means a couple of different things. So if you're looking for where your first derivative is increasing, that means that your second derivative is positive, and then my second derivative being positive means that my original function is concave up. Please excuse my dog chewing on his bone in the background. Okay, so if I'm looking for where your velocity is increasing, that means I'm looking for where my second derivative is positive, aka where my original function is concave up. So on this graph of my original function, I have to look and see where it's concave up, and I can kind of see wherever it looks like a valley. So from here, it looks like from 0 to 2, and then because 2 to 6 is concave down, it looks like a hill. So 0 to 2 would be where my velocity is increasing. Lovely. All right, if I have this problem, I have we're trying to find the maximum acceleration on the interval 0 to 3 by the particle whose velocity is given by v of t here. So one thing we want to look out for is that we're looking for the absolute maximum. You're looking for the maximum acceleration on this interval, and you're looking for it of your acceleration function. So I'm going to have to use my first derivative test at some point, but my first derivative test should be the first derivative of the thing you're trying to find the maximum for. And so here I'm going to take my derivative from velocity and I'm going to get acceleration. So 3t squared minus 6t plus 12. But then this is the function I'm trying to find the maximum for. So I need to perform the first derivative test on this function's first derivative. So I actually need to find a prime of t, 6t minus 6. And then I'll find my critical numbers, so I'll set it equal to 0, which means that t equals 1 is where I have a critical number. Then I have my sign chart here, and I'm testing things in a prime of t because I'm doing my first derivative test. And so if I plug 0 in or I plug 2 in, if I plug in 0, I get a negative number. If I plug 2 in, I get a positive number. So this is actually a local minimum. And so I'm not going to have my maximum acceleration there, okay? So I checked my critical points. The other place where you have to check for your endpoints when doing your candidates test, right? For a candidates test, you need to test your critical points and you need to test your endpoints. And that's the whole purpose of them giving us this interval, right? I'm trying to find the maximum on this interval, and your maximum can only occur at your critical points or at your endpoints. So we're going to go ahead and I'm going to find A of 0 and A of 3, and we'll see which one of those is the largest. And then I'm looking for the maximum acceleration, like the actual value, so my answer is going to be one of these numbers. All right, A of 0, if I plug it into here's my acceleration function, A of 0 would be 12. And then I also have to find A of 3. Let's see if I plug 3 in there. So I get 3 squared minus 6 times 3 plus 12. So I get 27 minus 18, which is 9. 9 plus 12 is 21, which means that my maximum acceleration I actually reach is 21. So D. All right, moving on to a particle moves along the x-axis so that at time greater than t or equal to t, its position is given by this function. At what time t is the particle at rest? So if my particle is at rest, that means that my velocity equals 0. So what I'm going to do is I'm going to find my velocity function, and I'm going to set it equal to 0. So here's my velocity function, 6t squared minus 42t plus 72. I'm going to set it equal to 0, and it looks like I have a GCF of 6t. So then I'll have, oh no, not 6t, just 6t squared minus 7t plus, what's that, 12? Yeah, wonderful. And then that factors into t minus 4, t minus 3, and so my particle would be at rest at 3 seconds and 4 seconds because my velocity equals 0. Wonderful. All right, I think we've already actually looked at this problem, but it's always good to review it again, right? So the graphs of the derivatives of the functions f, g, and h are shown above. Which of the functions have a relative maximum on the open interval a to b? So if my original functions have a relative maximum, let's draw a straight line there, that means that their first derivatives would have to equal 0 and change from positive to negative. So we're looking for which of these statements is true. If all of them are true, one of them are true, or none of them are true. So f prime of x does equal 0 at 3 places, here, here, and here, but it only changes from positive to negative there, which is fine because it does have a relative maximum. G prime equals 0 here, but changes from negative to positive, so that actually has a local minimum, so that's not going to work. And then h prime of x never actually equals 0, so that doesn't have anything, which means that our answer would be A. Only our original function has a relative maximum. Okay, these ones are calculator problems, and so it might be handy to have that out or nearby. So here we go. We have a particle moving along the x-axis so that at any time greater than or equal to 0, its velocity is given by this velocity function. And we want to know what the acceleration of the particle at time t equals 4 is. So let's go ahead and we'll find our acceleration function first. So a of t will be, it looks like we got a little bit of chain rule here. My outside function is 4.1 cosine of t. My inside function is 0.9 t. Derivative of the outside would be negative 4.1 cosine, or sine, excuse me. Derivative of the inside is 0.9. So my a of t, derivative of 3 is 0, so that just kind of goes away. Derivative of this would be the derivative of the outside. Keep my inside the same, times the derivative of the inside, 0.9. And I'm trying to find that at 4, so I'm going to find a of 4 by plugging in 4 there. Oops. And now I'll do that in my calculator. And I get 1.633. If you didn't get this, double check first and foremost that you plugged everything correctly, and then that your calculator mode is in radians, not degrees. We only use radians in calculus. So the first derivative of the function f is given by this, and then how many critical values does f have on the open interval 0 to 10? So we got to figure out critical values would be where your first derivative equals 0. So we're going to go ahead and you can set this equal to 0, or because we have a calculator, we're actually going to use our calculator to figure out where this equals 0. And so to do that, we're going to graph this in our y equals screen. So pull up your graphing calculator if you don't have a physical one in front of you, and you're going to click the y equals button. And then we're going to graph this in that first equation there. So you're going to type in your cosine. Oops. I would do parentheses cosine x squared, close those parentheses, squared, so that it looks something like this. Oops. There we go. Divided by x minus 1 divided by 5. Okay, so that's in our y1 screen. And then we are figuring out where this equals 0. So what you're going to do, and we're looking on the open interval 0 to 10, so we shouldn't have to change our window at all in our calculator. Just go ahead and hit graph. And then we're going to figure out how many times this crosses your x-axis. And now you might have to zoom in. So I actually am going to change my window. So W-I-N-D-O-W, window. And then I'm going to change my y-min, oops, so that it is 0, because we don't actually care, oh, not 0, excuse me, like negative 3. My y max I'm going to change to 3, and then my x min, that's what I was going to change originally, I'm going to change to 0. When you do that, you should get a graph on your calculator that looks kind of like this. So it comes down, goes back up, comes down, comes back up, comes down, and then just kind of like flattens out past that point. Okay, and so they want to know how many critical values does f have on the open interval 0 to 10. So I can already see automatically, I can see 3 of them. 1, 2, 3. Now this one for me looks like it could be very close, so it might be beneficial to zoom in even more in that section. Maybe make your y min -1 and your y max +1, just because that'll expand it a little bit more for you. When I do that on my calculator, let's see what it does for me. Yep, it actually doesn't touch here. So we would say that there are only going to be 3 critical values of this graph. So b equals 3. And we'll work more with calculators as well and practicing finding these pieces of them, but I just thought I'd introduce them at least a little bit. All right, we got quite a few more, so let's work our way through these ones. So let function f be the function with the, or let f be the function with the derivative. How many relative extrema does f have on the interval 2 to 4? So we're actually going to do the exact same thing that we did up here since we have access to a calculator. I'm not going to try to solve it if I can just have my calculator do it for me. So I'm going to go ahead and hit the same buttons and you're going to graph the same thing. The only thing you might have to change again is that window. So sine of x squared plus 1. And I'm looking between 2 and 4. So I'm going to change my window so that my x min is 2, my x max is 4, and I'm actually going to zoom in pretty far on my y as well, because your sine graph doesn't go very high, does it? All right, and so if I'm looking, it crosses 1, 2, 3, 4 times. If you graphed it correctly, you should have something that looks kind of like this. And that was when I changed my y minimum to -2 and my y max 2. So there are 4.